All right, so welcome to Just a Review. So your exam is tomorrow, and it's all show your work. So we'll go through this. So it's buffers, titrations, and the KSP stuff. And at the top of the review, it tells you it's either 11 till 2. Like last time, it's just you're showing up at 11 o'clock, and I will email it to you if and I will be on Zoom from 11 till 2. So even if you're not taking the test, you can come in, but you don't get to stay the whole time. You can just come if you have questions because I only have one person coming at a time. If you're going to do it at 6 o'clock, it will actually show up in the exam folder and you'll print it. And then in both cases, you'll upload it to the exam folder 3 hours later. So it is actually similar to the exam I've always given, and they've always had 2 hours. I actually think they had an advantage because they didn't depend on always looking through their notes. So they actually came to the test prepared. So I would tell you to redo your study sets. Some people said they're redoing their notes. I know the last test, the person who got the highest actually went back and listened to a number of lectures again. Because actually once you've already done some of the work, the lectures start sinking in more, and redid the notes with the lecture, and that helped a lot. All right, so you'll definitely see this question, and you see a question like this on the final about buffers. The thing is, on a true multiple choice, there is only going to be one answer. On this, there could be more than one. So the buffers are B and D on this question. There was one in the notes I know like this. So A is not because this is a strong. So strongs can never be part of a buffer. C is not because there's no acid. So is that showing up okay? I'm going to switch to green in a moment. What you need is a weak, can be a weak acid or base. It's every time I put my hand under there, it changes the focus to my hand. A weak acid and its conjugate base. Or you can do a weak base and its conjugate acid. So HF has been a question some of you have asked me about. HF is a weak acid. It was the very first page of the lab 4. It has a Ka value. All the other halogens are strong acids, and that would be its conjugate. It differs by 1 hydrogen. So just a reminder what conjugate means is 1 hydrogen. And then this last one is also. So this would be a yes for D, because that nitrogen, so this is a question a couple of you have asked me, the nitrogen makes it a weak base. And then this has the extra hydrogen. Again, questions that came up, this was the second page of your lab. If you see something with the nitrogen, you're thinking base, and the extra hydrogen gives it a positive charge, and then the chloride has a negative. So this is the conjugate acid. So that also works. So number 2 is we're looking for a buffer with a pH of 7.4. And 7.4, the best buffer is the pH is around the pKa. And you don't actually have to go and solve for the pKa. You just, they may remember, what's the easiest way, just looking at this without doing any math, that you know which one it is?
I'll look for the exponents.
Thank you, Jessica. Yeah, you look at the exponent. So this first one's an exponent of -3, so it's going to be a pH of 3, 4 in that range. And then the last one, pH of -13, it's going to buffer at a really high pH, like 12, 13. So our middle one is the one that is going to work at our buffer range of our body's pH. And that is a Ka, so we want this to be the acid, H2PO4. The conjugate base is going to be what? It's going to lose.
H2O4 minus.
Yeah, it's going to lose 1 hydrogen. So it's instead of H2PO4, it's going to be HPO4. and it would be a -2 or 2 negative. That's not a big deal. Sometimes you will see that if you write it like how I did, it will show the negative and the -2. They differ by 1 hydrogen. You could also add a sodium. So the first one would, and then you would lose the negative. So NaH2PO4, Na2HPO4. But that would be the buffer, the weak acid with its conjugate base. All right. Great. Now we move into the math. So there are some questions like that sprinkled throughout where you just give really simple explanations. I don't need lots of words. You can just say things like pH is around the pKa. The buffer is always weak with its conjugate. For 3A, I highlighted the part so you don't have to cross out my story part, but there are a few people who do appreciate the story part. We're trying to find the grams of ammonium chloride, and I gave you ammonia. So ammonia is NH3, in case you didn't know that. And ammonium chloride, what we're looking for is grams of NH4, and then chloride. So this is my acid, this is my base. There is no strong written in this question. There is no HCl and no NaOH. If you look at B, you suddenly see the NaOH. When we get to B, we will be writing a balanced equation. If you do not see a strong in the buffers and titration part in the whole pH section, don't write an equation. That's my advice to you. A buffer does not react with itself. They are both there in the solution together, swimming around together. So I gave you Kb. You have a choice always with buffers. You can always use Ka, or you can solve it with Kb. It will work both ways. In fact, try it both ways for this one, because it will give you good practice, and it only works that way with buffers because you always have both pieces. If it is an x squared problem, which we get to on the next page, you do not have a choice. All right, so do you want to do Ka or Kb? Do Kb for the fun of it? Okay, I'm going to do Kb. On the next page, we'll do some Kas. I need to remind you that the advantage of always using Kas, which is what they do for those who use the Henderson-Hasselbalch equation, which is fine. The Ka is hydronium, so you're already there. You don't have to do the extra step, but you had to do the extra step to switch Kb to Ka. So it's the same either way. I do want to remind you, you always state the formula that you're going to be plugging into. So for those of you who do it the way that I've been teaching, and a lot of you are doing it other ways, you need to state the formula that you are using to show what is going on, to show me you fully understand what you are doing. All right, so I just plug in 1.8 e to the -5. My acid is going to be this. So the X is on top. The hydroxide, if this is my pH, then my pOH must be 4.5. So hydroxide would be 10 to the -4.5. So 10 to the pOH is your hydroxide. You can do the same thing with pH. 10 to the pH is your hydronium. So that's where I just write it in like that. You can figure out the number, or you can write it in like that. And then in the denominator, I'm going to put my base. In this case, I'm going to write my unit. And do be careful here. Whatever my base is, my conjugate acid is going to be the same unit. So I'm in molarity. I'm going to keep it there. I rearrange. I guess I should have seen. Yeah, I solved it before. Kb. My X is my hydroxide. I'm sorry, my conjugate acid. Please always tell me what your X means when you solve for your X. I mean, I can sit there and figure it out, but if you're stating what it is, you're showing me you fully grasp the concept. You should get around 0.142. I'm not going to go through all the steps, per liter. So it's going to be a molarity like this one was. Actually, I guess I will. You would change your moles to grams. This is of the whole compound. So this is a conversation I've had with several of you. Whenever you go back to grams, the mass, it means you have to do the full compound. When we're talking about it aqueous, we're talking about it as ions. But when you go back to mass, it means you're actually getting the mass of something. So you have to add up the N, the 4 H's, and the Cl. So this would be, it looks like 53.5. Sorry, I scrunched myself. I'm used to having the whole board, and so, and then the volume. And that's another big question that comes up about buffers. The two parts of the buffers are mixed together. And so they both have the same volume. They're both mixed in the same 500 mils. So we just multiply by the 0.5 liters, and we should get my answer of around 3.81. Right, it is all show your work, so you want to make sure you show it in a nice logical place. The test, I think, is 6 pages because I spread it out more. So this I scrunched in. So I didn't give any of us much space. Make sure it follows. If you have step 1 way over here, step 2 there, it's all over the place. Please make sure you number your steps. Like this was really our first step here, and then we plugged in down here. This is my second step, and then there's my third step, stating the formula right before you use it. And questions? All right, next one, I'm gonna add NaOH. I just am in the habit of always writing the strong second because it's being added to. It's being added to the whole buffer, but only one part of the buffer reacts. So that, this is a base, it's gonna react with the acid. So a base does not react with a base. A base reacts with the acid, so NH4Cl. So the NH4 and the hydroxide will come together. And the sodium and the chloride, you can either cancel them out. It's a one-way reaction because we have a strong, right? The sodium chloride, if you want to keep them in there, they're at the end. So this is actually an interesting one. The NH4 and the OH come together, but they actually, NH4OH always breaks apart as soon as it's made. And sorry if you're hearing the airplanes that are flying in low over my house. NH4OH, for those of you who are in lab, I don't know if you remember this from back in 221, it always drove students crazy. This actually means NH3 plus H2O. So you can pull out the NH3 and you're left with an H and an OH. So yeah, it always comes apart. NH3 technically is a gas. And so when it combines with water, that's when it's in the aqueous and it's written like that. All right. So we do a mice chart. When you see a strong, you're going to do a mice chart. You guys know how to do this. So the 0.5 molar times its volume. I'm just going to set up the initial part of the mice chart. If it's a buffer question, your limiting should be the sodium hydroxide or the HCl. If it is not, go back and see if you have a place value off. So again, I'm not right there in front of you. You can absolutely sign on to Zoom. You probably want to have it click that you're ready, like, well, you just go in and sign in. It's easy. Please be patient. Again, I can only talk to one person at a time, and that please respect also when you come and ask a question, you don't get to sit in there for 10, 15 minutes. If somebody else is there, I'll let you know. So you'll, if nobody else is there, I guess you could sit there, but. So just be patient as you would be on a test. The NH4Cl we have up here. I'm gonna actually start with my answer, the 3.81 grams. And I know its molar mass was 53.5 grams to 1 mole. I did it that way on purpose because it's been a question that several people have said, how do you go from grams to moles? And I find it a really amusing question because you guys get all wrapped up and hyped up. How do you go from grams to moles? You learn that like the second week of 221 and you've been doing it for 3 terms. So grams to moles is really simple. You could also have started with the X value and multiplied by the volume. Either way. And then a reminder with buffers, there's no zero. Titrations have a zero, buffers do not. So there is a number on the other side initially, and that comes from up here, the 0.25 molar times the 0.5 liters. So you have an initial. The purpose of the M in the mice chart is it stands for finding moles, and so we get numbers. I guess I have numbers, 0.0125. If you guys want, I can pause and give you a chance to punch things in. I can pause the recording. People at home can pause. Or you should all, if you're watching at home, I would pause and try the questions. And I would recommend that you go back and try these again. The NH4, sorry, it should come out as around 0.071. Most of you are doing amazing jobs with your mice charts. So line them up nicely. There's some of you who make mice charts better than anything I can do. And you make these nice, neat rows. Especially those of you who have those tablets and you write on them so beautifully. My writing on them is not as beautiful. All right. So that's the initial moles. I recommend that you keep 3 non-zero digits. With that said, this must have been a 0 after this because I didn't write a digit. This is my limiting reactant. So I'm going to subtract that from my reactants. Please notice I'm showing units. And then on the other side, we add. So the 2 biggest mistakes made with buffers, 3 biggest. First one is having the place value in the wrong place. So if your strong is not your limiting reactant, I mean, you can come on to Zoom, but go back and see if you wrote a number, your place value off. The bigger mistake, you subtract from this side, you add to the other side. If your answer is not making sense, look at those things. And the other thing, there's no zeros. So there's an initial for everything. All right, so this will give us whatever number we get, right? We'll have numbers here. I always label. You know, I've done this for like a lot longer than all of you put together. And I do label. I'm amazed looking at some of your work, how you know what you're doing. So I label, oh, this time this is my acid and this is my base. And again, you can use Ka or Kb, just tell me which one you're using. But I always like to label my number, so I put it into the formula in the correct place. And you would solve, and you should get my pH of 9.63. And then you will be asked the question, does your answer make sense? So we added a strong base, the pH increases. pH was here, it was 9.5, it's now 9.63. If it did not go up, go back and see, did you subtract, did you add? There is another part to this answer. It's a buffer. So when you add a strong base, it went up. but only a small amount. So only a wee bit because it's a buffer. So it only went up by 0.13. It didn't go up a whole pH value. All right. And then let's look at the one at the bottom of the page, which is right from your, similar to the one that was in your lab. It might be the one that was in your lab. So the very first question, oh, is there any questions on buffers? I guess we're done with buffers for right now. And what's a buffer do? It keeps the pH from changing too much. So it maintains the pH, resists change in pH. That's what a buffer's for. We're made up of buffers. There's buffers all around us. All right, so we're doing the Goldilocks game, it looks like. So we have equal volumes, equal molarities. The key with this game is the moles are equal. So if the moles are equal, we have a weak base and a strong acid. If, notice I said if the moles are equal, the strong wins. So we have a pH below 7. A conversation I was having earlier with one of your classmates, you can use the greater than or less than sign. I recommend using arrows or writing the words or just saying it's too low, it's less than 7. And that's, you can use this as your explanation. The moles are equal, so the strong acid wins. All right, on the next one, they have the same volume. So several people asked me, you said not to do any calculations. How can we figure out moles without doing calculations? And they got kind of worked up about it with me. You can think about it logically. If they're the same volume, you have twice as much of the NH3. So you have 2 times the NH3 because they're the same volume. NH3 is a base. It is a weak base, but you have twice as much of it. We don't have 0.2 as much of it. We have twice as much. So a base means a high pH. All right, and then the last one, I can see right off the moles are equal. So you can always do the volume times the molarity, but this one, I have double the molarity of that one, and this one I have double the volume. So the moles will be equal. It's a strong acid, strong base. That is the only time you get 7. So the pH is 7. It is the equivalence point, the neutral point for a strong plus a strong is truly neutral pH. All right, so questions on this first page, one page down. So showing your work clearly. Again, on the test is more pages because it is spread out to give you more space. And make sure you have a calm and quiet place so you can stay focused. And I know some of you might be giggling at that, but you all have the ability to do that. All right, I'm gonna move on to this titration page. So CO2H, that's an acid. And I know it's an acid because I'm adding NaOH. And so let's write our equation. C6H5CO2H plus your NaOH. So again, those of you listening at home, I would stop me right here. I would try this problem and then listen to it and see if, I mean, you can fast forward me, but you can also listen and see if there's anything I mentioned that you want to keep in mind. This is the hydrogen that comes off. So on organic compounds, we write the carbons and hydrogens first, right? And that's going to combine with the OH. So we get C6H5CO2. That has a negative, so it's going to attract the sodium and H2O. A reminder, the sodium in organic chemistry, sometimes they show it after because it's attracted to the oxygen, or sometimes they show it first, truly show cation, anion. It doesn't matter to me, but this is our conjugate base. You can label that if that helps you. And this was our weak acid. And you're going to do a mice chart. I'm not going to do the full mice chart. My answer is there. To see. Done this. Oh, yes, we're at the equivalence point. So what we know is we have 0.675 grams of this guy, and we'll change the grams to moles. Right? You guys know how to do that. It's 100. Add your carbons, hydrogens. Make sure you have a periodic table, your calculator. So whether you're doing an 11 or 6, that you have your place, you're all set up, and you'll get some number of moles. So 0.00553. So the NaOH, I didn't give you a volume. Do you use the 60 milliliters? What are you going to do? Well, it is at equivalence. The moles are the same. That is the whole point of equivalence. You just need to know one of them, and you know the other one. So these guys are equal moles. So they actually cancel out. You can make your full mice chart, or you can recognize, okay, as soon as I know one, I know the other one. They completely cancel out, and it's completely moved to the other side. And this is where half of you got it wrong, because you stopped showing units. And then you just assumed you were in molarity, which you are not. So this is the conjugate base. That's all we have. This is x squared. Since it's a conjugate base, you're going to have to use KB. You would state your formula. And right, you're going to do 10 to the negative 14 divided by your Ka. You would state your full formula right before that. And we were going to do x squared over the conjugate base. But we can't use that number. We have to first find the volume. And I know what the volume is because I did. There is one more step. And that is, if we take this many moles, this is our moles of NaOH, there is a step where you have to find the volume of the NaOH. Moles divided by its molarity will give you volume. So like for me, I didn't give myself enough space. We'll put it over here. We'll label it volume of NaOH. So a lot of you on your lab, you had stuff all over the place. Clearly label. Show me you understand what it is. That lab was to have you practice titrations. And the students who practice them, once you get them, this page of the lab or the test, a lot of people are like, oh, I know I got that page. I know I got it. And like I said with the last, at some point last week, a lot of people, this ends up being their highest exam of the year because they get the titration and the buffers. But you would take the moles, and we're going to divide by the molarity. And that is going to give you some kind of liters. It looks like it's 0.0265. That's not the number that's going to go down here. It's at 5.5. You know what? This is only 2 5s. Sorry, that's me. 5.53 moles. This needs to be the total volume. We have this volume. We need to add it to this volume up there, the 60 milliliters. So I have 0.0865 liters. What I would tell you all is to make sure you go back and redo these. And when you do them, practice showing your work in a really nice, lovely fashion. Like my mistake I can see already is I started in the middle because I'm trying to teach and I'm used to having my board having more space. So make sure you give yourself enough space. So this is the total volume. Now the biggest question that came up, just in the interest of time, I left, like you'll probably have a step before this and it will give you, let's say 20 milliliters of NaOH. So there'll be a step before the step A. And you're like, the question was, do I use the 60 and the 20 and this number? The 20 milliliters would just be at one point in the titration. You never use that number again. So every volume of NaOH is just for that question. Like here when we get to C, we will use the 33 milliliters. We will not come back and use this 26.5 milliliters. All right, you go through the whole thing. I'm gonna go this way. You get your X, which is your OH, and you keep going, you find your POH, and it makes sense because it's a conjugate base. pH should be above 7. All right. I want to go through the chart. The chart, I know a lot of you are getting the chart finally. The chart is meant to help you because once you get the chart, the titrations make a lot more sense. So this number here is going to go in, it is the conjugate base. It's this guy. This is my conjugate base because it's the one missing the hydrogen. So this number is going to go in that box. And apparently that's 0.0639. Remember up here, it was partnered with the sodium. So you can absolutely cross the sodium out. It does not affect the pH, but I left it in there because I knew the box was coming up because I could see it on my page. So these two were partners. All right, you found an X value. The X was the OH, so this is your X value. This also is your X value, the very first box in this case. Because if you wrote your formula for Kb, Kb is conjugate acid times hydroxide. So since it's X squared, 2 of the answers have to be X. All right. And I have 3.2 e to the negative 6. So you should be in that ballpark. The hydronium you can find one of 2 ways. Change your hydroxide to hydronium, or you can just do 10 to the negative pH. It's just found the pH. You just take it back a step. So that's that piece. Questions? Again, I'm going through it because I'm trying to point out stuff. I would show my work a little bit more neatly than this. And so go back and practice showing, doing the titrations and walking through them calmly, how you want to be when you're taking the test. All right, so we're now going to add 33 mils of NH3. So write your equation. I recommend you do write the equation. A lot of you are super duper smart and you're leaving out the equation. So that's up to you. The advantage of the equation is then you have your chart right there and I can see everything's labeled. If you don't show an equation and have it nicely lined up in the chart, you're going to have to label the things to tell me what all these numbers mean. All right, this number, this initial number of your weak, either weak acid or weak base, that is that number, 0.00553. That's the number in the titration So the ones in the lab, you did multiple steps for each one. That's that number that just keeps showing up again and again. But this time it only shows up here. The NaOH we're going to figure out, right, with its volume times its number up there, the 0.2085 molar. So that's how we're always doing the NaOH or HCl. And we already know it's going to be higher because our equivalence point, we're past the equivalence point. So 0.00688. In a titration, your other side does start out 0. So that is the difference between buffers and titrations. Buffers, there are no zeros. Titrations, you do have a 0 to start with. This is my limiting reactant. So this guy's gone, right? So you can subtract. This is where a lot of students will add to the other side and do KAs and KBs. You don't need to do that. You can do this part. This was my starting. This is how much. And you're going to get a number here. And I recommend you label it, because by you labeling it, that's going to make your head go, I know what this means. This is excess of NaOH. And why that is special is it's NaOH. The sodium doesn't matter. This is excess hydroxide. We're ready to go right to POH. You don't need a Ka or Kb. You can just do negative log of the hydroxide. If it's excess of a strong acid, you can go right into negative log of the hydronium. But there's a problem. And that is moles, clearly showing my unit. The only time you can leave it in moles is if you have a buffer. And that is on this previous page. I could leave it in moles because I have something on both sides of that are related, that are conjugates. Once you get equivalence, x squared, once you get here, and also with all the KSP stuff. All right, so our volume. Well, I have, this has to be over the total volume, just to remind you. I have 60 milliliters that I started with. That volume stays there. And my new volume. And so the question so many of you have asked, and I've been waiting for that question, and so thank you to all of you who have asked it. Well, what about this number? I figured it out up here. Like in the lab even, there was one where it was a special box where you figured it out. That was only at one point in the titration, and now we've moved on. So we've used that number. We used it in step A. We actually even used it in step B to figure stuff out. And so then we move on. And this whole piece, the molarity, plugs into the hydroxide. The answer makes sense. And many of you worded this not well. You said, yeah, I keep adding hydroxide, my pH goes up. Oh, it did not go up a little bit. Remember on the previous page, the wee bit was 0.13. This went up 4 whole points. It goes very high because you have excess of hydroxide. So the answer I'm looking for more is your pH is going to end up either very high or very low because you're at the excess point. All right, half equivalence. There's a reason you only get a little bit of space because this is really simple. And when you get to half equivalence, you're like, I got it. And yeah, I will try to tomorrow be in my office hours by 10:30. So if you're planning to do it at 11, you just have a few questions. You can also just say, hey, I just want to ask them, usually, but the pH equals the pKa. So all you have to do at the half equivalence. I want to show you why. because several of you have asked this question and then it made sense. And it becomes your favorite part of the titration is the half equivalence. The half equivalence means half of the 0.00553 reacted. And so the acid is half, and now the conjugate base is the other half. So the acid and conjugate base will cancel out. So your Ka is your hydronium. If you're doing it with a Kb, your Kb is your hydroxide, and you're good to go. All right. Questions before we do the curve? And so many people every year, oh, I don't know how to do the curve. I don't know how to do the curve. Can you do it again? You guys have an advantage. You have a huge advantage. You just go to YouTube and you can rewatch that little segment of the video when I drew the curve. Yeah. All right, we're going to start low. It's going to have a gentle slope, but it does have a slope. And then there's a cliff. And then it pretty much flattens out. It's not perfectly flat, but it's pretty much flat. So you have a gentle slope. We are going to label pieces. Label your axes, pH. This is the volume of the NaOH. Let's go ahead and put the points we did on this. So our equivalence, we figured out a volume. So your graph is not going to be perfect. Maybe it will be, actually. It's a nice way of knowing if you did your stuff right. And the pH there was, what, 8.5. It is in the middle of the cliff. So that was probably the biggest error with your guys' pH curves. I don't know if somebody in tutoring, if you were just guessing, if there's some online site that just has things wrong. Because believe it or not, that happens. I'm sure none of you have ever run across anything in the news or online that's just wrong. But it is in the middle of that. It's not the top or the bottom of the cliff. This is what, 8.5. All right. We're going to do another point. We're going to do, well, we can do the excess, right? This was over here at 33 milliliters, and we're at a pH of around 12. So we're in the flat part. That flat part happens at 26.55. It pretty much, those of you who took 221 had the lab experience, that was that one drop more. That did it. All right, and then we're going to do the half equivalence. So I think the problem, this is not a good question, I just realized, because it makes the pH at the half equivalence look like it's half. That is totally a coincidence. The half equivalence is significant. It is half the equivalence points volume. So if this was 26.5, you guys have your calculator or you have your brain cells, this would be 13.25 milliliters. You are in the gentle slope. Oh, look, we're halfway on the gentle slope. This cliff happens at this point. It really is 1 or 2 drops. And there's 20 drops in a milliliter. It's pretty much straight up. And so this gentle meandering, and that was what, 4.2? So we'll go down here. This is around 4.20. My initial, we never figured it out. So you can just say, oh, it must be around 3. You know it's lower than 4.2. It's not going to be significantly lower, but it is some. There was a gentle slope. It's not going to be way down at 1. It was a weak acid. Weak acids don't have pHs all the way down at 1. Many of you, when you did the cabbage juice lab, you said, I couldn't get red. How do I get red? You would have had to go to Home Depot and buy some muriatic acid, which is HCl, or go take some stuff out of your car battery. that's the idea of the curve. I want to do the opposite curve, which is the one that was on your lab. So on your lab, you started high, you had a gentle slope. That's why some of you had like kayaker, and then you hit the waterfall. It is straight down, and then it flattens off. So it mirrors. Equivalence point is there, halfway down the waterfall. Half equivalence is there, halfway along the gentle slope. So questions with that? So this would be the weak base plus the strong acid plus HCl. And this was our weak acid plus NaOH. If you're having trouble falling asleep and want to listen to one of my lectures, which would be that first titration lecture, actually the first titration I did was a strong plus a strong. So here we go for the question. How would a strong, so HCl plus NaOH. So instead of starting with this guy up here, we're going to start with HCl and we're going to add NaOH. And we're going to assume the moles were the same, the 0.005553. How would it be different? How would it be the same? What do you want to do first?
Wouldn't you have like a straight line instead of a slant?
Where would you have a straight line?
Across near the bottom where the pH is.
Yes,
low.
And you are right. And actually, before I do what you just said, I'm going to use a different color. There was something else I wanted to label on our curve that we have. This is more for all of your information. Down here, this is where you have the weak acid and the conjugate base. They are both present in the gentle slope. This, several of you were in my office hours, or I wrote this on feedback. This is the buffer zone. The pH, we're adding NaOH. It is going up, but it is going up very slowly because you're in the buffer zone. It's buffering the change. It's barely changing. When you get to here at the equivalence, you only have the conjugate. So in this case, the conjugate base. And then up here, this is where you have the excess of, in this case, the NaOH. And so that's, and the other place is initial, is only the weak acid. We wrote all this before. It's probably in your notes. It's probably a mess. I recommend listening, going back. You don't have to listen to the whole lecture. You can find the part where we did the titration curve, and you'd probably go, oh, now I get what she's saying. So what Catherine just said is it would start out, there's actually one other thing about where it starts out, is it's going to start out lower. So this would be the HCl will start lower. So why is it going to start lower?
Because the acid is stronger.
Yeah, it's a strong acid. It is a strong acid. Strong acids completely dissociate. So you're going to start lower, and it barely changes. We used to actually do the calculations, and we would get to 26.49, and the pH would still be hardly have changed at all. So those are two big differences, that here you don't have a buffer happening because it's a strong and a strong. So the strong acid's still winning, so it just stays low. You still have more strong acid. So this is where you still have more strong acid. Now, there is one other piece that's different, but I'm going to talk about what's the same. Is you got a straight up and down cliff. After equivalence, post equivalence, it's the same. And the reason it's the same, after the equivalence point, it doesn't matter what acid you started with, it's now all about the base. Megan, you were here earlier. I remember you were one. There were a couple of you who you stopped your titration curve at the equivalence point. If I went past the equivalence point, you're going to go past and show the nice flat line. So the top is flat because it's a strong, the bottom is flat. And it's a sharp change at the equivalence point. It's straight up and down. There's no gentle sloping happening. It's really 1 or 2 drops changes the pH as you're going from which one is excess and that point. The other big difference has to do with equivalence pH. And we just did this on the other side. Equivalence pH of a strong acid plus a strong base is 7. Why is it 7? Well, the hydrogen and the hydroxide neutralize each other, and we are left with sodium chloride. You're left with table salt. This is the question. So Brianna, if you listen to this, this is a question you asked me yesterday, kind of casually. So sodiums we keep canceling out, even when we get to the KSPs in a moment. Sodiums also do not affect pH. So the 1As we got to keep crossing out with everything we're doing. Her question came up with something with the KSPs, and she said she kept crossing the chloride out. With KSPs, you cannot cross chlorides out, but with pH, the chlorides don't affect the pH. So sodium chloride doesn't affect pH. All right, that's all I got for right now for pH stuff, unless somebody has a question. We're gonna move on. You ready? Or you can ask me this evening, tomorrow. Yeah, actually, since I still have this here, what if we did NaOH plus HCl? Up here, we'd start higher. It would be flat, like Catherine said, and then it would drop. And then after, it would be the same. So you have straight drop, and then it flattens out. All right. I'm going to move on. Always go back. It's not erased. And we're going to do some KSP stuff. I'm going to shorten some of this. I feel like this is out of focus. All right. So calcium, the first step you do for every one of these, write your equation. Calcium's a +2, so we're going to have 2 hydroxides. Write your KSP. If you do not write this equation and your KSP, you will lose a point on every single one of these questions. You actually might lose more. So write your equation, write your KSP. So the OH is squared, and then see what you're going to do with it. All right, we're calculating the KSP. I will give you KSPs on these so that we all have the same KSP when we're doing the test. Online again, depending on what website you go to, you could probably find 50 different KSPs for calcium hydroxide. So if it tells you the pH, if the pH is 12.4, then the POH, you also know, because it's 1.6, right? This is a question Erin had asked me either end of last week or early this week. I don't have to see that step. You can just state it like that. pH equals this, POH equals that. I'm pretty sure at this point, it was a comment I made 2 weeks ago, and everybody, having done this for years and years and decades, people look at me like, these log questions are so crazy. And now it's so second nature to you guys. You just automatically can do pHs and POHs. 10 to the negative POH will give you your hydroxide. So 10 to negative 1.6 is the number that we plug into there. You do not double it because that is the hydroxide. What you have to do is for the calcium, you would have to cut it in half. Because the calcium, if the hydroxide is double the calcium is half of the hydroxide. You can ponder that. You can think about that. That's your calcium. That's your hydroxide. You will square the hydroxide and you will solve for KSP. Question number 2 in your study set was very similar. Yeah, and you know what? It is the same question. It was calcium hydroxide. I get these questions from different books, and it's a different KSP. So again, KSPs vary with temperature, with who experimented. So just, you get it. You're being graded on showing your work more than the answer, since it's not multiple choice. All right. We're going to do PbCl2. So you would write your formula. This one, right off, will precipitate. Well, first thing you should do is write your equation. Lead and chloride. Write your KSP. Do it. All right. Will a precipitate form? This is a Q problem. And this is one where the volume is changing. So for the PB, you can either do it over here. I just do it underneath. You're going to take that initial amount of PB. So get rid of the little m. It's e to the -3. And it might be because we are doing this online, so I don't have to hear all you guys moaning because you're all muted. Because students usually like, wait, how'd you get to the -3? And you guys have been very calm because you've been like, oh, that little m just means milli. It's just how it is. It is a unit. It is legit. What we're really doing is M1, M initial times initial volume, which is the 200 milliliters. You can change it to liters or you can leave it in milliliters, only because we're going to cancel the volume out and we're going to divide by the total, which is the 300 plus the 200. If you're ever unsure, go to liters. But since we have milliliters over milliliters, they cancel. You're going to do the same with the chloride, right? Not going to go through all the steps. You had one of these on your worksheet. I'm pretty sure everybody got it. Oh, a few of you missed it on the worksheet, and every single person missed it for the same reason. They forgot to square the chloride. You do not double it, but you do square it. And you get a value for Q. So I wrote my Q down here. You compare them. So if you remember, you do the alphabet. You can sit there at home in your room and sing the alphabet. It would be good for you. And our K is greater than Q because 10 to the -8. You can write it out longhand. Just take a deep breath. The alligator points us forward. Forward is the ions. It's aqueous, no precipitate. That when it says explain, do your thing, whatever, this is all I'm looking for. So I want to go back to something that happens on these two, because this is a big conceptual thing. On this number 7, you do not double the chloride, because we brought the PB and the Cl from 2 different places. The PB came from the lead nitrate, the chloride came from the HCl. So they are not stoichiometrically related. Up here, it's a saturated solution. All you have is calcium hydroxide. The way you know all you have is calcium hydroxide, it doesn't mention anything else. All right. And the other thing, kind of glazed over on number 7, hopefully you did too. What happened to the nitrate and the hydrogen? Why did I ignore them? Why didn't I write a whole equation with lead nitrate and HCl? Well, nitrate is always a spectator. That was Nick. Nick is here. He'll be hanging out while you guys are taking your He's a really big Nick, so he's a little scary. He's like giant Nick today. It's like the marshmallow guy in Ghostbusters. All right. Hydrogen's the 1A column in the KSP stuff. So your test, can't remember now, it is segregated. So the KSP stuff is all together. So I guess that's another advantage. So you would show all your work, you get to your answer. This one, you do have to, you would write out your equations, and we do have to solve. This one, because you would have a lead and an iodide, it would be KSP, you have x, and then this would be a 2x squared. So this would be 4x cubed, and this one you would have KSP equals x squared. You cannot just look at the KSP if you have different ratios of ions. So Alexander, this was the one you said you liked when we were doing it earlier. So you want to figure out which one precipitates first. You solve for x. And what am I asking? Which precipitates first? The smallest x is going to be the least soluble. KSP, the S stands for solubility. It means how much is aqueous. It's all about equilibrium. It's back to the very first lecture. We only look at gases and aqueous. Solids don't matter. So this, the smallest, is going to be the least soluble, which means it is the most precipitate. And so that must have been the silver. I'm looking at my answer key over here. Yeah, so the silver is going to win this one. So this one goes first. So you would want to explain to me. I also would remind you to please make sure you read the question, because half the time I ask which precipitates first, and half the time I ask which is most soluble, which will give us the opposite answer. So just make sure you read. Advantage you have, again, is it is all show your work. As long as you explain it carefully, I don't need lots of words. I don't need complete sentences. Scientists don't like complete sentences. They like just simple symbols. All right, number 9. I just keep going unless somebody has a question. Somebody at home probably has a question. All right, how do I know what my precipitate is? Is it the sodium sulfate? No, because we see sodium. Cross it out. Is it the silver nitrate? No, nitrate is Nick. Nick is always swimming. So we have silver and we have sulfate, and they're going to go together. So our precipitate is silver sulfate. Silver is a +1. It likes to be a +1. It is why, if you have your periodic table, if you have, those of you who had made, the periodic table we used had the old numbering way with the B's. It is why silver, copper, and gold are called the 1Bs, because in Mendeleev's original periodic table, they were actually with the 1As, the alkali metals, because they behaved like them. The old way of numbering periodic tables actually had a lot of history to it. This is your solid. This has actually been really good review of ions, in case you haven't noticed, of stuff you should have learned way back in 221. And so you should feel comfortable with them. But in this case, the only anion that I'm going to be giving you to cross out is nitrate. There are a couple others that are always soluble, but I'm not going to throw those curveballs at you suddenly. And for the cations, the positive, it's anything in that first column of our periodic table. So hydrogen, sodium, potassium, lithium. All right, we know the silver. The silver is 0.022, so the sulfate is X. The silver gets squared, you solve for X. X will be moles per liter of your SO4. And then from that, you can go to grams. You are not going to grams of silver sulfate. You are going to grams of sodium sulfate. So this is back to questions. Some of them came up last night, some this morning. And people were saying, asked, but we crossed the sodium out. Why are we suddenly putting it back in? So we're adding sodium sulfate to this liquid, to 250 mils of the solution, sorry, to a solution. And so when you're adding it, the sodium and sulfate are together as a solid, which is the grams. As soon as it hits the solution, the sodium and sulfate separate. The sodium keeps swimming around, the sulfate finds the silver and precipitates with it. Anyway, questions before I flip to the back side? We have 3 more. All right. So this question, Juliana, if you're listening, this was the one you were asking me earlier today. So once you get these, go back and redo your study set. And yeah, today office hours usually aren't very crowded, so it's a good time to come if you have specific questions. Also a reminder, especially if you're here now and you haven't talked to me about when you want to do your presentations, because we're focusing on the test for tomorrow. Absolutely focus on the test. Oh, next week comes early. You have a nice weekend. Your guys' presentations are next week, Tuesday and Wednesday. So please talk to me. All right, we're gonna write 2 half reactions. I'm gonna start with my solid. You guys know how to do this. Split it into the ions. And this has a KSP of 4.5. On these, with the half reactions, you don't have to write your whole KSP little formula of zinc times hydroxide squared. All right, the second one, the second half reaction has the solid on the product side. And so we start with the ions. Zinc is a positive 2 charge. It likes to be a 2, combined with 2 OHs. And so in the net, which was up here, the zinc's canceled. Since we flipped the equation, we're going to do 1 over the KSP. So we're going to do 1 over 8.0 e to the negative 12. And then you multiply these. So our final piece kind of depends how you show it. Our one that has the solid to aqueous is on top, and the one that's flipped, its number is on the bottom. And you solve for K net. This is not a KSP. This is our final K. I give you a number there. This K is less than 1. It's 10 to the negative 6. So the reaction goes reverse. And in the reverse direction, the zinc hydroxide is your precipitate. So, questions? Last page of your study set had those. Your study set key, I had some distractions earlier this week. I apologize. I didn't write out all my equations because usually I'm doing it on the board for the whole class. So, all right, so we get number 11. Only thing you have is barium sulfate. You have nothing else. That means these guys are X and X. It is not a Q problem. It is how much precipitates. You cannot use this mass. So this is an important question. It just says you add this to water. It's not telling you how much of the 1.234 grams dissolves. It's just saying you added it. The KSP tells you how much dissolves. You solve for X squared, that's moles per liter. You solve for grams. That's how much dissolves. And then you do your subtraction, your 1.234 grams. This is your total or your initial or your original minus the blah, blah, blah grams that dissolves. And you will get how many grams precipitates. So this is where we're going. KSP always tells you how much dissolves. So if you're asked how much precipitate, you're just going through it and then you do a subtraction. Just make sure you line it up nice and clean. Questions? All right. We also know that they are stoichiometrically related, and same with this last one. Aluminum is +3. I know that because I know my periodic table. You guys should have one in front of you when you're doing your test. Again, the test has always been 2 hours. And so I would not wait until 2 minutes before the time's up to try to upload it. I would just do it and be done and turn it in and move on for your weekend. All right, it wants to know how much dissolves. So if this is X, this is 3X. There's nothing else in the problem, there's only the aluminum hydroxide. I did this one because I wanted to remind you, it showed up on your worksheet. When you set it up for KSP, you'll have X, and then you'll have 3X, and it is cubed. So 3 cubed is not 9. That's usually when I do this live. 90% of the class is giggling because they had all made it 9. At some point, it is 3 times 3 times 3, so it's 27, and there's now 4 x's, so we get 27x to the 4th. We solve for x, and you know what to do. This does not have a subtraction, and you get your answer. That is how much dissolved. So make sure to read, is asking how much dissolved. But what I wanted to point out was a question several of you have had. These are stoichiometrically related. Go back and look at them. All that is present is the aluminum hydroxide or the barium sulfate. If you go back to the ones on the previous page, number 7, number 9, you were mixing 2 different things. Like here, you suddenly have sodium sulfate added to silver nitrate. And on 7, you had the lead nitrate and the HCl. All right. Any questions? I'm going to stop recording, and just again, if you're in Take It Easy 11, I'll try to have I'll try to get in my office about a half hour before that to answer questions. I'll be there tonight, but you got to come to my office hours because the test will be emailed to you, and then you will upload it. And if you want the data study, 6 o'clock, you just go to the folder. It will suddenly appear at 6 o'clock, and you do the test, and then you submit it by 9 o'clock. Yeah, if you know you have a slow internet, make sure you start uploading 10 minutes before. All right, I'm gonna stop recording unless somebody has a question.